All right, we're going to talk about solving trig equations. And in order to talk about solving trig equations, we need to talk about the inverse trig functions. And there's essentially only three of them. Um, Inverse sine, inverse cosine, and inverse tangent, right? As you can see, I've put sine, cosine, and tangent. And I want you to take a look at how the inverse graphs, how the inverse functions are made so you can understand some of the special rules we're going to have to use with it. Okay? So, if we talk about sine, sine is a sinusoidal graph. It oscillates up and down forever and ever. Its range is from -1 to 1. Its domain is all real numbers. Okay. When we talk about an inverse is just you take the input, you take the output, and you just switch them. It's that simple, right? So if I had a point at, I don't know, pi comma 0 right there. If I were going to invert it, it would be at 0 comma pi, which would be somewhere right around there. That's all I do to get an inverse point, right? And the reason why I do that is because I'm asking it, the purpose of the inverse is if I know what my solution should be, I use the inverse function to have it spit out what the original input was, right? So my goal is to kind of work backwards, hence the inverse. So, keeping that in mind, we need to talk about the fact that sine is not an invertible function, meaning that if I took the inverse of the sine graph, right, I would have it oscillating up and down this way forever and ever. So it would never pass the vertical line test. Another way to kind of explain that is through the horizontal line test. So if I draw a horizontal line as best I can, because I don't have good motor skills, you see that for each of these inputs, which is represented by the horizontal line, there's more than one for each of those outputs, right? Which is represented by the horizontal line. They're outputs. There's more than one input. That's how I know it's not invertible. Because if I tell you that sine should equal a, I don't know, 1/2, well, there are multiple answers to that. And that's not allowed for a function, right? Because function has to be 1-to-1. So here's what they did to kind of work around that. They decided, okay, cool. So we can't do that. So we're just going to focus on this bit of the graph, right? From negative pi over 2 comma -1 to pi over 2 comma 1. That bit of the graph is going to get inverted. So that means every single point in there will have its x and y value switched, its input and its output switched in order to create the inverse function. And here's why they did that. The range for a sine function goes from -1 to 1. It goes all the way from -1 to 1. So that'll cover every possible output that the sine graph could have. So the inputs can be determined from there. And here's how they did it. They talk about arcsine. So when you see arcsine, that's another way to talk about the inverse of a sine function. Note it is not the reciprocal. That is something different. This is the inverse, right? So 0, 0 stays at 0, 0, but notice this endpoint is -1 comma negative pi over 2 compared to this point that was negative pi over 2 comma 1. So I'm just going to erase this part for you so you can see a little better. Okay. I will leave the little marks though in terms of where it starts and where it kind of stops. So I have this point, I have that point. this stretch of the graph from negative pi over 2 to pi over 2, from negative 1 all the way to positive 1, is inverted to create this black inverse function. Notice the x and y switch. Same thing over here. X and y's switch. That's it. So when we talk about arc sine, which can be written another way, and let me show you what it is. Arc sine of x, which can also be written as sine inverse of x, if you remember your function notation for inverses from integrated 3, has a domain, right? The inputs for the inverse function should go from negative 1 to 1. The range, aka the outputs for the inverse function, will range from negative pi over 2 to pi over 2. That's it. So in a later video, we'll talk about how do I use this information to find solutions in a certain interval of, yeah, okay? So that's true for arc sine. So I would say pause the video, jot this down, because you're going to have to use this as a reference, okay? So if that's true for arc sine, then let's talk about arc cosine, which, as you may or may not have guessed, will be the inverse for the cosine function. All right, so we have cosine here. Okay. So for cosine, it's the same idea. What they did was they decided to go from this point to this point, because that's the maximum, that's the minimum. So they'll cover between 0 and pi all possible outputs that a cosine could have, and they'll find an angle that will produce that between 0 and pi. So if we talk about arc cosine, of x, I wish it wouldn't color code like that. Let's make it black. Right? It takes 0, 1, places it to 1, 0. It takes, oops, you can't see because of my stupid head. Dang it. Pi, negative 1 goes to negative 1, pi, right? No, I don't want that. There we go. Inversed right here. Inversed there as well. So they took that stretch and they just inversed it to create arc cosine in the black. So if we talk about arc cosine, which can also be referred to as cosine inverse of x, the domain, right, the possible inputs we could have for the arc cosine are this. It can go from negative 1 to 1, and its possible outputs, the range for the arc cosine, should be from 0 to pi. Right? And that's true for arc cosine. Same idea as what we were doing with tangent, just arc cosine. I don't want to dwell too much because it's already kind of long. So now let's talk about tangent. All right. So, oh yeah, if you didn't pause it, make sure you pause this video, take these notes down because you're going to have to refer to it. My bad. Okay. So, tangent. Let's go ahead and erase what we currently have. So tangent is a little different. So for tangent, again, it's not invertible because if we took all these points and we kind of did that, it would fail the vertical line test. It fails the horizontal line test right now. So here's what they did. They decided that between right there in that part of the graph is where we're going to do the inverse for tangent. So I'm going to go ahead and say that I can't really do points here because it's kind of like infinity's involved. So let's go. Change this from arc to arctan. Whoa, not what I was expecting. Okay. So, arctan, which I'm going to get rid of the tan graph because it's kind of hard to see. Maybe. Okay. Arctan has these special characteristics. And let me erase this part. So, here's what I know about arctan. Which is also known as tan inverse of x. Its domain is actually all real numbers, but its range is from negative pi over 2 comma pi over 2. So if you notice for this one, I chose not to use brackets because tangent does not exist at negative pi over 2 and it does not exist at pi over 2. So as a result, if tangent doesn't exist at these values, then its inverse should not exist at these values as well because it's impossible to have these as inputs. So how would it have negative pi over 2 and pi over 2 as outputs for the inverse when it didn't exist in the first place? And again, take the time, write the notes down. When we we'll talk about cosecant and secant and cotangent, like their inverses later, because as long as you know sine, cosine, tangent inverses, you can use those for the reciprocal of secant, the inverse of cosecant, the inverse of secant, and the inverse of cotangent. I have to be careful because reciprocals are not the same as inverses, so I have to be consistent so you guys don't get confused.